Good afternoon. It's David Eastwood, Geotech Engineering and Testing. How are you doing, you guys? Today, we're going to be talking about forensic evaluation of commercial and residential structures. Let's see. Get it all set up here. Okay. Get the spotlight. Yeah, we got that. Put that back here. Well, welcome to our forensic seminar. Let's see if you can move on. A little bit about our company, Geotech Engineering and Testing. We're located in Houston. We've been in business for about 36 years. We do geotechnical, environmental, materials, and geoforensic engineering. We've got a staff of 60 people, of engineers, technicians, geologists, support staff. We work all over Texas, Louisiana, New Mexico, and Oklahoma. And one thing we have our own rigs. We can get out there and do the work quickly. We're full service. We have our own lab, everything. So you can go to our website and see some of the documents in here. Audience, we got about 215 people RSVP'd, and lots of engineers, a lot of people from different cities all over the state, university, civil engineers, a lot of structural engineers. If you need to reach me, you can reach me at David D.E. at geotecheng.com or 713-699-4000. I work 6 days a week, so I'm here. Okay, a lot of stuff that I'm talking about here is on our website, and you can go to the YouTube channel and you can go on the search under Geotech Engineering and Testing. And this presentation and others going to be on the YouTube channel. If you have any questions, go ahead and type it in the Q&A section, and I'll answer it as we go through. So I want to make sure everybody can hear me. Can everybody hear me? Let's see if you can get an answer here. Let's see. Okay, well, I'll presume everybody can hear me. So what we're talking about here is all kinds of projects. Could be a school project. This is City of Houston command station. And let's see. This is on Wellcrest. The whole, the whole bottom of the floor slab has come up and the walls are bowing. And so it's been fixed now, but that was a few years ago. This is residential projects, foundation problems. This is a typical crack on projects. And so got hairline crack on it. Here's the Italian guys can build a structure, but they didn't do a proper geotechnical work on this thing here. It's tilting. It's not good. It's a typical design screw up and construction screw up. There's another one. This is Rice University. You see the CMU wall is just all cracked up and everything. See the hairline cracks here again in the CMU wall. Brick cracking. This is an apartment complex. You can see the wall. It's got center lift. It got the basically opening at the top, and of course the crack gets smaller as you go down. Yeah, you can see the crack in the brick in here. You got the cracks and separations in here. It's a commercial building. More separations. The this is a strand area out there in Galveston. That was a kind of interesting picture there. It's a brick cracking here. More brick cracking. This is a church out there in Bel Air. City of Bel Air is a church. It's got a bunch of cracks in their brick. This is a grade beam hairline crack. Sam's Club. Floor slab cracking. Walmart, floor slab cracking, got alligator cracks. Foundation, here's a crack. You put your hand in there. It's kind of crazy. More separations, shrinkage in the soil, cracks in the brick. Here you get more sheetrock cracking, separation, sheetrock, floor slab cracking, door not being square. Hairline crack above the door. Sheetrock cracking. You say ceiling tile cracking. This is a medical facility out there in Stafford. The whole thing was cracked up. It's more sheetrock cracking. More sheetrock cracking. Ceiling tiles coming off because of the wall movements. This is that City Houston command station on Willcrest. You see the walls are bowing in here. This is a school out there in Tyler, Texas. The whole tiles are coming off the walls. Doors not square. Doors are not square. We can't, you know. Here's that medical facility out there in Stafford, and it just moved so much that it broke the glass, so people could not get in. I mean, people just stopped using the door, just went through the window. You know, walls hovering, floor slabs separating from walls. Here's a spread footing failure. They had foundation problem with this structure in here. They went out to put a spread footing on top of the expansive soils. That whole area is heaved up on the floor slab. So you got to watch out for that. Heaving. Subdivision distress. They're building these subdivisions and they have poor drainage and water comes out and the area kind of settles, you know, the sidewalks kind of settle because the soils are so soft because it's always saturated. So you get sidewalks out of whack. Here's the front yard. Spread footing. Subdivision distress. We talked about those. Here's the kind of a Montessori school out there in Willcrest. No, it's not like a Derry Ashford. We couldn't close the door. It's just everything was moving so bad. We couldn't close the door there. Moisture coming through the slab. You can see that. Yeah, this is the whole tiles are coming off because of so much moisture. Here's the moisture bubbling under the tile. This guy here went out there, put moisture barrier. Put moisture barrier here under the slab. He didn't put moisture barrier here. So this area stayed wet. He asked me what to do. I said, I don't have any answer, man. You got to get out there and deal with it as is, but it's a safety hazard. If you bust the concrete, you go underneath there, and you will see water. It's a perched water table underneath that slab. Water just sitting underneath the slab in the sand layer. It's called perched water table. Tile distress is a tile separation from movement. More tile cracking. Here's a corner grade beam cracking out there in separation. This is not a structural problem. This is because of the absence of bond breaker between the brick and concrete and thermal expansion and contraction. So the way you fix it out there, you go in there and put a bonding agent and with non-shrink grout and rebuild your end of your grade beam. This is basically the brick. And this is your gray beam when it's a bond, absence of bond breaker. You know, they start moving and they start cracking. Slope failure. This is a slope out there in Memorial. It's a doctor house. And the whole backyard left. They put concrete bags in there, made the slope heavier so it fails sooner. You can see the whole backyard gone. Here's another one, landslide. It's a house sliding downward. Parking lot cracking out there near Buffalo Bayou. Retaining wall failures. This is after Harvey. This is San Antonio retaining wall. It's a block wall system. And they didn't check proper global stability on it from what I understand. And you can see the whole backyard's failing. A lot of people have to be moved out. These are houses out there on Lake Conroe. Beautiful houses out there on Lake Conroe on 105. And you go out there, they start digging a ditch in here, channel, to connect it to another channel over here, so that they can put their boats in. And then they didn't consider the effect of the retaining walls. So after starting, digging the channel, the retaining walls start failing. After that, the whole backyard start failing. See the grass out there in the backyard, the pools start moving. And so it was a very interesting project. You see the cracks out there and the flat work. This is another job out there in League City. And on this one, the bulkhead is failing. So if the bulkhead is kind of moving here, so the whole backyard starts moving. You have these beautiful landscape areas of the pool. You can see the crack starts forming here. More cracks. Backyard starts moving. Backyard starts cracking. Dispersive soil conditions. We have a lot of dispersive soils in Houston area. Dispersive soils are the soils that are easily erodible when they get wet. These soils contain high percentage of sodium salt ions. And you can see that right there. You can see these little tunnels in here that are created by washout of the fines and soils kind of eroding away on our channels. These are dispersive soils. Jug holes. These are dispersive soils pictures. This is a Project Veterans Memorial and Beltway 8. They had a lot of erosion on the detention pond over there. And they had these holes in there because of the dispersive soils. The cops were chasing somebody out there. One of them falls into one of these holes, breaks his back. And they go around and start suing the homeowner association, the civil engineer, the geotechnical engineer. Everybody was sued on that deal. You can see guys stuck in there. Buffalo Bayou got this beautiful golf course out there on San Felipe. And but it's right next to Buffalo Bayou. That's the golf course. This is the Buffalo Bayou. Meandering like this. They went in there and put geotextiles here to make it green and everything, take care of the erosion, but they didn't check for global stability. So after they put the fabric in, everything started failing after a rainfall. The slopes start moving. That's the golf course there. It's a bunch of attorneys. Bulkhead failure. If you go out there, 610 Loop West near exit Woodway, there's a bulkhead like that and just moving away, it's failing. This is the bulkhead failure out there in Colorado River in Montgomery County, in Matagorda County, where we had a rapid drawdown where the water went up and then went down, saturated the slope, and the whole thing went. And these are the anchors coming out. Here's another one here. You got a port facility on the Gulf Coast, and they didn't design this thing properly. The ship comes in, they want to unload gravel. They start unloading the gravel, the whole thing starts failing. They say they designed it for like 200 PSF, and they loaded it to almost 4,000 PSF. Building failure. If y'all go to China, they had this building here sitting on piles. What they did was in these on this building, they start excavating in the front and putting in the back, create a surcharge with global stability, came in and broke the piles, and the building starts falling. One thing we have a lot in Houston area in Texas called geologic faulting. You build the structures on the faults. Here's the fault. They start having cracks. Pools. We have a lot of pool failures here and there on expansive soils. They're out of level. Some of them hydrostatically get pushed up. Punch through failure, a parking garage. It's the columns right there. Here's the deal out there in Dubai. Start excavating, and the water starts seeping in here. I told them, hey, watch out for this thing here. This thing can get big. The guy was here sitting here in the crane. Water was coming out. They didn't do much about it. The whole thing broke. Guy was still sitting there. Crane failures. We're running into a lot of these crane failures. We're going to have a whole new presentation on these crane outriggers failures. This is a 2-yard concrete, about 8,100 pounds. They were delivering it in the medical center. It falls on the guy's leg, cuts the leg off. This thing only, 18 inches by 12 inches. And bad situation there. This is Whitney Lake slope failure. That's near Dallas area. You can see the crack out there in the rock. Starts failing. House starts falling out. Something closer to home, efflorescence. You see that on the brick. Outside the brick, it's got high alkaline, cement, mortar. You can see that. To have efflorescence, basically efflorescence is a fine, white powdery deposit of water-soluble salts left on the surface of a brick as the water evaporates. To have efflorescence, there must be a water-soluble, there should be water-soluble salt present somewhere in the wall, and there must be sufficient moisture in the wall to render the salts into the soluble solution. There must be a path for the soluble solutions to come through to migrate through the surface where the moisture can evaporate, and thus deposing the salts, which can crystallize and cause efflorescence. So with this solution, basically the efflorescence is caused by alkalis of sodium sulfates and potassium sulfates. Use low alkali Portland cement, which has a 0.6 alkali or less when you do the brick construction to reduce the chance of efflorescence. Concrete pavement distress. We see a lot of concrete pavement cracking, distress. No steel. Again, area. This is a nice hotel out there. Marriott on 610 Loop. Joint failure. Cracks in the paving. More cracks. Concrete deterioration. You see the manhole and all the concrete just deteriorating. More distress. Here the fines coming through the cracks, turning black. The soil is coming through. Separation in the joints. Flatwork cracking out there at Willcrest. Parking lot distress. Asphalted concrete, pavement distress. See all the alligator cracks and potholes created in the parking lot that they didn't do any base. They just put asphalt on top of natural soils. No stabilization, no base. And the asphalt starts cracking within a year. So what is failure? Failure is defined as a foundation, structure, component, or facility that doesn't perform as intended. A failure does not have to involve a collapse or catastrophic event. Some examples are foundations that exhibit excessive differential movement, parking lot that ponds water, roof that has excessive deflection, masonry wall that cracks because of lack of expansion joint, basement walls that leak, pools that are moving up. But basically most of the failures are not on the evening news, but they're important to the building owner who has to deal with it, and the contractor who has to repair it, and the engineer who gets sued. And of course, the attorneys make all the money. So the way you evaluate distress is a scientific approach is you state the problem, perform observations, formulate hypothesis as the cause of problem, test the hypothesis by observation, analysis, physical tests, analyze the results, make conclusions, develop a damage model. Damage model is when you do forensic evaluation, you say this building has failed, and so to stabilize it, you're going to go put in some helical piles. You're going to need that many helical piles. Is going to cost $1 million to fix it. So damage model tells you how much damage caused and what's going to cost to fix something. Qualification of the forensic engineer. Got to be an expert in what he's talking about. Formal education, experience, licensed engineer, active in technical societies. Fair, impartial, and ethical. Truthful, objective, avoid conflict of interest. Let's see if you can get it. Must like to be like a detective. Someone whose job is to discover information crimes and find out who's responsible. You have to be able to think outside the box. You have to enjoy digging for the truth. Must be a good communicator. Be able to do reports, deposition, trials, all that stuff. So the matrix for failure for foundations is right here. This is the basically you look at design, inadequate soil report, inadequate structural design. We look at construction. We look at materials. We look at maintenance. If the concrete was good or bad, materials, maintenance, is there trees there? You got bad drainage or something else? Wear and tear is like sewer leak, plumbing leak. Inadequate geotechnical reports. And I review a lot of geotechnical reports, and they don't describe the site properly, some of them. Incorrect bearing capacities, the pier depths. There's a certain way to calculate pier depths for piers on expansive soils. Remember, the lighter your structure is, the easier for it to heave. So somebody says, well, I don't have any load on this thing here. And that's bad, because the lighter your structure is, the more it's going to heave up. Incorrectly estimated movement values of PVR, inadequate information regarding perched water table, inadequate structural design, did not discuss foundations and risk with the client, unfamiliarity with the proper design method. Like F.PTI has got a real detailed design procedure, so you got to know about foundation design with soil report. Come on, man. We're in 2022. You can't have foundation design without soil reports. Misapplications of the design to the site condition, slope sites, sites on active faults using wrong type of foundation for the soil conditions. Here's the important deal. Engineer of the record should have adequate information, including drainage, slope, existing trees, future trees, and vegetation prior to foundation design. Inadequate construction. So we go in there, you got this building's got problems, we go out there and jackhammer right next to it. See if it's got piers. So we go out there and excavate. We measure the beam depth. What's the depth of the beam? Measure the width. If the design says your beam should be about 30 inches and you got 24-inch beams, you got a problem with the stiffness of that slab. If your beam's supposed to be 12 inches wide, it's only 8 inches, you got a major stiffness problem. And you can see the beam, grade beam measurements. You check for the pier to see if there's a pier right there. You drill a hole out there to check for the pier. And we check with the pier to see if there's a bell. Here's the shaft of the pier. This is the grade beam. And you can see that. And here's the bell. Measure the distance from the shaft to the bell. If it's 12 inches, for example, you got a 36-inch bell. If it's 20 inches, you know, so you may have 20 times 2 plus like 12. That would be 42-inch bell there. Again, you measure from the shaft to the tip of the bell. You may have to excavate the whole pier, and if you excavate the whole pier, you may see a spot here. There's a separation between the bottom of the pier and the shaft. What that tells me is that pier is being lifted up by the expansive soils. And it's lifting up the superstructure, which means that the piers are too shallow, they're not deep enough. That's the void there. If you got a job where you got piers that are connected to grade beams and it's heaving, that means the piers are too shallow. It's a pier grade beam connection. Now, if there's a separation between the top of the pier and the grade beams, that tells me the piers are deep enough and basically the grade beam is being lifted off the floor slabs. Here are some sound walls in Pearland, Friendswood area. These are Hector project, and you can see how the piers are moving up. Here's the piers are moving up. Column distress. Make sure you got joints around the columns. The columns move separately from the floor slabs. They have two different types of movements. So typically there are joints around columns. Otherwise, you're going to see a bunch of cracks around columns because the floor slab moves, and so you're going to have problems. Columns are basically stationary. So you develop basically joint cracking. Floor slabs, when you put floor slabs in, of course, make sure you put control joints in them. And the columns got to have the isolation joints in them to allow the expansive soils to lift the floor slabs and it doesn't have to develop cracks around here. So you put this fabric around it as basically as a joint. A lot of times on tit wall buildings, for example, you got anchor bolts. And these are like joints out there around columns. Instrumentation. If you want to know crack movements, you put crack monitors on the walls. It shows this is a two-dimensional. It shows which way it goes. Measures the movement as a function of years. Here's another crack monitor here. Shows the separation. Here's the crack monitor. Here's a three-dimensional crack monitor. It shows three-dimensional movement. There's a three-dimensional. Non-destructive testing. You can do ferroscan to see if there's a steel in your slab. A lot of times the steel may be all the way in the bottom or there's no steel. It scans, uses electromagnetic field current, and it runs it through on the slab. Shows where your steel is, what size of steel you have. Here's the one we did out there. It shows number 5 bars and spacing of 10.5 inches in X direction and 8.5 inch in Y direction. So this direction is about 10.5 and this Y direction is 8.5. It's a medical, this is a metal building. They want to know if there is a steel in their floor slabs, what's the concrete thickness, record the existing paving just to calibrate our machine width. And when we did the scan, ferroscan on it, we found steel spacing of 12 inch, 11 inch, 12 inch, 13 inches. And basically the specs call for rebar spacing of 10 inches. So they were more than 10 inches. And then say minimum cover on the concrete should be 2 inches. In this case, are 3.2, 3.3, 3.1 on the concrete thickness. Sometimes we find steel all the way on the bottom of the slab. It's not good because the steel is not doing anything now. It's all the way on the bottom of the slab. Sonic testing, sound travels through concrete, roughly about 10,000 to 14,000 feet per second. From that, you can calculate the concrete pavement thicknesses using the sonic device. You just got a bottom plate that hits the concrete, sends a sound wave, comes back. From that, you can measure the time and velocity. And from that, estimate the concrete thickness. It's the device. You calibrate it with some cores. You do actually some cores. This is the floor slabs. You go ahead and do some cores. First, you do cores. You calibrate the core thickness with your machine. And you can see in here, basically the floor slab is supposed to be 6 inches. You got 4 inch, 4.2 inches, 4.7 inches, 4.8. So it's nowhere close to about 6 inches where it's supposed to be. Somebody's got a question. How would it be possible to increase the volume? My speakers are at their max, but I can barely hear your presentation. I don't know if I can increase my volume anymore. Check your computer because everybody else can hear me well. Is there a problem with anybody else hear me? Because I think that's just your problem. Okay, here it says you're fine. No. Everybody says they're fine. So the problem is with your system. So everybody can hear. Let's see. Done. So, and you can see that the concrete is 4.3 inches. ACI has got a tolerance requirement, ACI 117 for slab thickness, plus 3/8 and minus 1/4, which means that your concrete thickness should not be more than 3/8 of an inch from your spec. So if your concrete slab is supposed to be 6 inches, it should not exceed 6.638 or should not be less than 5.75 inches. The same thing, we did sonic testing out in the parking lot. Core it, concrete, calibrate it with the machine. And here's the concrete, supposed to be 6 inches. It's 5.2, 6.1, 6.89, which if you compare it to the ACI 117, it does not meet basically the thickness requirements. So, so you can use non-destructive testing to estimate thickness as long as you calibrate everything. Geotechnical, drilling and sampling. We do borings next to trees. Trees tell us how to design foundations. We measure root fibers when we drill. Borings next to buildings. And root fibers tell us how deep your oxygen and water exist and defines your active zone. Your active zone is usually about 2 feet below the depth of the lowest root fiber. So if you got a job wood, your root fiber is at 10 feet, then your active zone is about 12 feet. So we go out there and core the concrete. If your core drops, there's a void underneath your slab. That means your pad is separating from your slab. If there's a crack in your slab, you go out there and look at it through the hole underneath. This is your crack under the slab. Your pad is separated from your slab. This is the space. This is your grade beam, your crack. So your vapor barrier is deteriorating. So after coring, we go out there and look at the concrete. There's a crack out there in the concrete. We get soil samples. Here's a house in Seabrook. Had foundation problems. You drill holes, see what kind of soils you have. They didn't do a soil test for it. They did put it on piers at 8 feet. The whole house was moving around. So we drill holes out there, got samples. That's what the clay looked like, highly expansive clay soils. We run elevations. This is a zip level elevation that you run on your slab, and you get elevations throughout the whole slab matrix. And you get a contour of what everything looks like. You run elevations. And measure the deflection. You can also, when you build stuff, you can put these cables in it. There's a group called Steadfast. You put these cables in your grade beams. And if your slab moves, these cables tell you to a computer system how much movement is experiencing. So you put the cables in the grade beams. And basically you pour the concrete and you connect to the cables here and connect to your you can computer, and you can see contours of movement of your slab. Texas A&M is usually doing a lot of that this system because there's a lot of movement on their slabs out there in A&M. If you got a house that looks like this, it's a brand new house in highly expansive soil area, and you see that kind of deflection of the floor slabs, minus 0.2, minus 2.4. Is this thing heaving or is it settling? Highly expansive new house on expansive soils. Is it settling or heaving? Well, it's heaving. On 95% of the new construction on expansive soils, heaves up. We usually don't have any settlement. Settlement occurs usually after 10 years. So on new construction, most of the problems are due to heave. Here's another building over there. If you look at the floor slabs, this is plus 325.5. The whole thing is just moving down this way, this elevations. This is another building. And if you look at it inside the building, these areas have heaved, the gray areas have heaved. They've heaved as much as 1.4 inches from a low area of minus 1.8. Roughly about there's 3.2 inches of movement. Here's a tail wall building out there on Richmond Avenue. When they built this thing, was on heavily wooded sites. You can't, basically the whole thing is just moving. Tail wall panels are coming out. You look at this floor slab movement. Minus 7.8 plus 3.3/8. Heaving over here. Piers are too shallow, out of levelness of about 4.25 inches. That's what the slab looks like, a three-dimensional. This is the HISD school. You can see this thing is moving. This is elevations -7, elevation of -0.5, that's 7.5 inches in differential. Outer levelness, you can see -1.5, 3.0 -4, -5, -6. It's really out of level. Here are some concepts. Tilt. Tilt is planar rotation measured over length or width of the foundation. Slope. Differential elevation between 2 points divided by horizontal distance. Okay, so you can have up to 1% tilt. If you have tilt, the whole thing is rigid, so you're not going to have distress. Okay, so this is a house, they ran the elevations on it, and you got the contours that are all parallel. That means the house is tilting. That's why you don't see any cracks in it. You can have 1% tilt. That means if your house is 50 foot wide, you can have as much as 6 inches of tilt. Deformation, change of shape of foundation after original foundation construction. Deflection ratio, deflection, maximum deviation from a straight line between 2 points. And deflection ratio is the deflection divided by the horizontal distance which occurs between them. So that's a correct deflection for points 1 and 2, 1 and 3. It's the correct deflection. This is not the correct deflection. It's not correct. PTI, Post Tensioning Institute, it's got a guide for performance elevation of slab on ground foundations, where you measure elevations. So we basically say elevator 360, which means that deflection limit of 1 inch in 30 feet. And you can have a tilt of up to 1%. So this is a house out there on Lake Travis in Austin. You run the elevations of the floor slab of the first floor. You get a section BB in here. You run the section on the program, and you get elevator 563. That means it didn't deflect that much. So the floor slab passes the first floor. And the tilt measurement shows 0.38%. That means that it passes. It didn't tilt that much. You do the second floor. You run the numbers. It's elevator 318, which means the movement is too much. So it failed the movement, but the tilt is 0.13%. It passes. These are TRCC performance standards. That's the Texas Residential Construction Commission. They're not in business anymore, but a lot of their criteria is still being used in litigation. Floor slab cracks should not be more than 1/8 of an inch. Floor flatwork size cracks should not exceed 1/4 of an inch. Flatwork separation, expansion joints should be less than 1 inch. Stairs 3/8 of an inch. Settlement, carport, garage separations maximum is 3/16. Sheetrock cracking 1/32. Brick masonry 1/8. And can't read this. The joint gaps in the brick mortar should not exceed 1/4 of an inch. Okay, some of the remedial measures to reduce heaving of the floating slab. Here's that the slab moves if it goes from a total wet to a total dry, or from a total dry to total wet. If you limit the moisture movement, then there's not going to be any movement occurring. You can use a sprinkler system all around the structure, put space between the dryways and exterior grade beams, have positive drainage, and use sand. Do not use sand when you set your foundations in the forms. Remove the expansive soils, replace with non-expansive soils. So if you got a site with
active zone of 10 feet, PI of 60, you're going to have to remove 7 foot of soil to get your PVR to about less than 1 inch, which is not economical. Nobody does that. Here's a building here. You can see this area has got grass. This area has got concrete. So you can develop cracks here because this area starts moving and this area doesn't move. So you develop cracks here. Same here. You develop cracks here because this area moves and this area does not move. It's a blockbuster deal. You can see grass all around it. It's a uniform moisture around it. So the whole area is subject to movement. Here's a house. When you put a driveway, you put a space between the driveway and the wall. Don't put a driveway next to the foundation system. This provides a horizontal moisture barrier. This area doesn't move, but this area where you got all this wax leaves, planter areas, this area moves. So this area moves. This area doesn't move. So you develop cracking here. You can put concrete all around your structure. That prevents it from moving after the initial movement. You got horizontal moisture barriers all around the building. Benchmark construction. If you really want to know how much your building is moving, you put a benchmark in the ground. And you drill a hole in the ground about 12 inches, about 20 feet deep in Houston, about 25 foot or so in San Antonio, Austin, and Dallas. You put your helical pile in there. This is the stem bar. You got to separate this bar from expansive soils. So you put a PVC pipe around it. You grout in between the PVC and the hole. This is your bar. Grout it. So the bar is not moving because it's below 20 feet. Then you open it and you actually run the elevations from the top of the bar here. That's your benchmark. Benchmark does not move, so you can develop actual elevation contours on your building. You can go every 3 months, run the numbers, and you see how your slab is moving. This is November, August, March, and you can see the elevation movements. Perched water table. Parts of Texas, we got these sandy soils over the clay. So when it rains, water just sits there in the sand and cannot penetrate the clay. That's the perched water condition. And the soil is saturated. So when you go out there and start digging your grate beams, you can get filled up with water because of the perched water condition. The water is underneath the foundation system. This is the pier here, and you see water coming all around it, just sitting there. Again, you dig next to a foundation, it gets filled up with water. These are perched water table that's just sitting underneath the foundation system. Piezometers. If you want to know where the water is underneath the slab, you can put piezometers in the ground. You drill a hole, you put a PVC pipe in there. It's perforated PVC pipe. You put it in a hole, put sand around it. Then you measure the water level in the PVC pipe. So how deep is the water? In this case, it's 7 foot deep, 10 foot deep. So that's a piezometer there. It's a piezometer outside. You measure the water depth in here. It's about 5 feet. So the interior of the building and exterior building can have different water levels. That's a piezometer construction. This is your screen. You put sand around it. Then you put bentonite seal, and above that, you grout it to the top. That's how its piezometer is sticking out the ground. Lift-off testing on post-tension slabs. If you want to know if the cables is alive and he's carrying load as in tension, you do what's called a lift-off testing. Lift-off testing is to verify the design force of the tendon has been achieved. On occasion, situation requires lift-off to be performed. This can be done due to elongations being out of tolerance. In addition, sometimes specification require verification of force in the tendon. So what you do, you go get your tendon over there, you open it up around the whole grout pocket here. You grab it here and start pulling on it with a jack. Make sure you got at least 26.5 kips of tension. You basically do 3 tests on each side of the slab. Brick. We got a lot of structures with brick cracking. And that's because of absence of brick joints. Here's a big building here. There's only one joint in here. That's a joint to the brick brain. You know, here's another building that's all cracking up because there's no brick joints. There are brick joints here. Brick joints. Brick joint spacing should be a 20-foot spacing for bricks. We need to have expansion joints in brick because brick and all building materials expand and contract with changes in temperature, humidity, and other environmental conditions. Because these materials move at different rates because nature will put them in if you don't put them in. So you ideally on brick jobs, you put brick joints at 20 feet spacing. Where you put brick joints periodically in long walls, all offset in walls where the short run of the masonry meets the long run, and outside corners where different materials meet. Let's see if I can read this. At junctions with different functions and different heights. Okay, materials. So you got a concrete slab that's cracked up. See what to do. You don't know what to do. Maybe the concrete strength is bad. Make sure the soils underneath is sand and bad soils underneath the slab causing heat. Then reinforcement steel is not good. Record that concrete. Measure the thickness. This is the vapor barrier here. Check for the steel location. So the steel locations. You break it. It's supposed to be 3,000 PSI, but it breaks at 2,000 PSI. It fails. Basically, ACI says concrete in an area represented by core test should be considered structurally adequate if the average of 3 cores is at least 85% of F.C and no single core drops less than 75% of F.C. Additional testing cores extracted from the locations presenting by erratic core results then shall be permitted. So if you can design a strength is 3,000 PSI and you get 0.75 or 2250 and 85% average is 2550. If your number drops below 2,000, 2250 for one of your cores, you got bad concrete there. Let's say you have your concrete string passes, but you still got all the cracks. You do what's called petrographic analysis of concrete, ASTM C856. You got a cross section of that concrete core. You take a section of it like this. You put it under the microscope, add blue dye to it. You study it. Look at the water cement ratio, air voids. You see you got air voids here. You have no air voids here. You got water cement ratio 0.55 to 0.6. Typical water cement ratio is 0.4. So that means the concrete is wet. It was poured real wet. So that's why you got all the cracks. The string passes, but you still got wet concrete. You look at aggregates, around the gravel, the aggregates. This is calcium hydroxide crystals, and the paste of the aggregate interface. This is calcium hydroxide. Now here you got the black spots in here. That's clay. That means your aggregates were too dirty. We check it for air voids, chemical attack, alkyl-silica reaction, where basically ASR is reaction between a certain aggregate types with cement that forms a gel that can cause excessive expansion and cracking of the concrete, where you can see the gel in here. This is your aggregate in here. Maintenance, drainage. You look at the drainage here. You want to have positive drainage from your building. This is not acceptable. This is not acceptable. This is not acceptable. This is not acceptable. You want to have positive drainage everywhere. This is not acceptable drainage. Not acceptable. Not acceptable. Not acceptable. You know, out there, if you go out there and drive out there on Gessner Avenue, you can see all these landscape architects that have all these mounds out there. All the water is driving, basically flowing towards the building. And these buildings have movements. All this negative drainage. You see the negative drainage here. Okay, here's the building in Stafford. They got pea gravel here. And it's very permeable. So when it rains, water goes in there and causes the heave of this building here. It's all cracked up. So pea gravels are not good. Don't put pea gravel around your building. You want to have positive drainage away from your building. Positive drainage. Positive drainage. Positive drainage. Guys, a question. What's the best way to remedy flat or negative slope of a backyard or personal residence? You can either do regrading or you can put area drains. I'm going to get to that in a minute, but area drains. Again, positive drainage. Put the trees as far as you can from your building. These tree root systems can cause settlement of your building. Bed liners. Don't put gravel and topsoil in the bed liners next to your foundations. Here's negative drainage. The bed liners get saturated, filled with water. Water sits next to the foundation, causes heave. And you can see here negative drainage here with topsoil, not a good deal. Don't put topsoil next to foundation. Bed liners. These bed liners hold the water next to the foundation system. Keep it all saturated and cause heave next to the foundation. These gravel stuff is pretty bad. You can see here they put gravel here with bed liners and the sprinkler system next to the foundation. And it's not all over the foundation, it's just partial parts. So these areas causing heave. Here's out there in Brazoria County Commissioner's office. You got gravel, topsoils, highly expansive soils that can cause this building to move up and down. This guy's got a fish pond next to his house. Not a good idea. AC units. This is a house in Tanglewood. The house was heaving up on one side where the AC units were. That's because of all the condensation from the AC units that just water just dropping and wetting the ground next to the wetting the ground next to the building and causing it to heave. Gutters. This is not a good gutter. It just drains and hits in the soil, creates void underneath the foundation. This is a bad construction. Again, this is an HISD school, low maintenance. You know, see the hole in here. The gutters are missing. Again, more problems with maintenance. HISD schools. This is a gutter going to underground drainage system. That's good. You get that water away from the roof line coming through the gutters to an underground drainage system. Getting that water away. Here's Alan Sattler building out there in Conroe. You can see that he's dumping the water on the paver, which is pavers are permeable. So it would be better if you had an underground drainage system. So I don't like that because the pavers have got cracks in them, the joints, and water can get in there. They got here, you know, basically very long splash boxes here, getting the water away from the building. Here, the gutters dumping in the grass, but they got concrete here. So this area moves, this area does not move. So you develop cracking. Here, going out there, concrete, the gutters draining onto the concrete, which is fine. Here, the gutters go into an underground drainage system, which is the best. You take it to a sump pump system. It's the gutter. It's underground drainage. Here's the gutter coming in, drain at the curb line, which is fine. Get that water away from the building. Here's a building at near the Bush Airport. It had the sloping roof, and all the gutters were on one side only, one side. So this area just was wet and causing heave. So the whole east side of the building was all cracked up. So here's a house on 1488 out there, south of Conroe, and real sandy soils and good drainage. When it rained, didn't have gutters, water would just drop off into the bed liners and just hold against the foundation. And it smelled bad inside because perch water table under the slab, it was just water just sitting underneath it and smelling. So we need to get that water away from the building. Here's the water just sitting out there next to the grade beams. You can see in here, when you don't have a gutter, when it rains, water just creates a depression next to the foundation. And if you have expansive soil, it can cause heave. This area here, the doggy was hot and he dug out the hole, keep cool. Here's another one that the doggy excavated. In areas where you have not much sunshine and you don't have grass growing, the people put pea gravel or gravel in here. Make sure that gravel, the ground underneath the gravel is sloped away from the building. Make sure you have some area drains. Don't let it just dump in here because you can't see it in the gravel. It's permeable and just water just sits there. So make sure you got positive drainage everywhere. If you got gravelly stuff, get the gutters, go to underground drainage system. Because this area just gets wet and just water just sits there. Put area drains in small areas with poor drainage. Gutters overflow when you design the gutters. If they're too small, you get overflow in one location and causes heave that part of the building. Olive Garden restaurant out there in Conroe, if you go look at it, they're building these Olive Gardens with rock, mortar, very rigid structures. They have these bed liners and gravel. If you got highly expansive soils, water just sits there and causes heave. So I just took pictures of the Olive Garden planter areas, and the manager comes out there and says, well, what are you doing? I said, I'm taking pictures, initial pictures before it starts cracking up. The gutter system comes over here, dumps in here and take it there. The gutter comes down, goes to an underground drainage system. That's good. Area drains in areas that you got small drainage areas and you cannot drain easy. You put some area drains in there. These are area drains. These are area drain here, I guess. Put a French drain next to the building. They put them in there, I guess, for termite control, but that holds water next to the foundation system and can cause heave. This is a building in Fort Bend County out there. Used to be old Andy Meyer's office. You see the skirts in the building, and they got sprinkler system all around it. They put this little skirt to keep the movement from lessening the movement. They got sprinkler systems all around. These are the sprinkler systems. If you put them in, put them all around. Don't put them in just some areas. Here and here, you got a planter area with a sprinkler system. This one here, no, nothing. So this area can cause heave. Check the soils in the planter areas. Do not use topsoil. Current practice is they go out there and dig next to the foundation and put these sandy topsoils next to the on top of expansive soils next to foundations. When you put these topsoil there, the sandy topsoil, it creates a perched water table condition next to foundation and causes heave. Grading, make sure you grade the whole area with clay away from your building before you put your grass in or anything else. You can put a couple of inches of sand, put your grass on top of that, but grading should be done with clay, positive drainage 5% away from your building. So all your drainage kind of be established with clay soils. Make sure you don't put pea gravel out there next to your planter areas, in your planter areas next to your building. This is a building in Bel Air. The back of the house was heaving up. They didn't know why. They removed some of the wood in the patio. They found a bunch of sand out there. That sand was holding the wall moisture next to the foundation, causing heave. Structures on slopes. We do a lot of projects with structures on slopes. God bless us with Buffalo Bayou. A lot of the buildings next to Buffalo Bayou, if they're not properly designed, they fail. Some of these columns are not any good. These are just basically man-made columns by, not engineers. They're not engineered columns. Some of these columns, if they're slow, they're shallow, if the building starts moving, they start cracking, develop high moments and shear at the top. Again, you see the houses on slopes, buildings on slopes, movement and sliding, slope failure. This is Tomball, and the whole backyard of the houses are going into the ditch. Got a slope failure. You build buildings next to big slopes. Make sure you put them on deep piers. And here's a landslide next to the house. This is a house in Arlington Court subdivision next to Memorial Park. Notice the space between the buildings is like, this space is like 3 feet. 3 feet here. You can't get any equipment back here. This back patio was separating from the house and moving down the slope, creeping down. They had a little bulkhead in here, retaining wall didn't work, started moving. They went in there, put sandbags in here, concrete bags. Because they get heavier, start moving more. So all the columns starts tilting. The patio got separated from the house. We told him to sell the whole thing and get out of the place as is. There was no way you could get equipment back there to get it fixed. This is a house out there in Memorial. This was a dentist house. The backyard was terraced. After they build a house, the slopes start moving, starts cracking the slab. Major lawsuit. Contractors were never, were not there to be found. They went out of business. Global stability. When you build houses or buildings on top of the slopes, you got to check them for global stability. if you put them on foundations, you can have a slope that goes underneath the foundation and causes it to move, called global stability. Swimming pools, we got all kinds of swimming pools around Texas and around the world. Natatoriums. The world's largest swimming pool is in Chile. It's $1 billion deal. These are all the hotels. Real expensive. Oh, these are pools that come in many types and shapes. A lot of beautiful landscape architects. They don't design them right. Look at this pool in here in Tanglewood. And you can see water is coming up over here. Why is that? Why is the water coming up on the left side? Well, that means because the right side is heaving up. So we see a lot of these pools out of level. And that's because of poor design and construction. Not doing a soil test, and you can see this side is coming up. This is a pool in Friendswood. This is one side of it. Here's the other side. It's out of level. It's a pool in Memorial. It's called Vanishing Edge Pool. And you can see there's a 40-foot drop in here. They didn't account for it, so the edge of the pool cracked and separated. Start going down the slope. Here's a pool out there in West University. They cleaned it on a Saturday. They emptied the pool. It drained. The hydrostatic pressure pushed it up. Here's 15, 17 inches out of the ground. They sued, but the insurance company said, hey, you are the ones who were trying to clean this. You did not relieve the hydrostatic pressure. The pool still is sanitary, safe, and livable, so we're not going to pay you anything. I got a question here. Thoughts on urethane injection on pools? We level pools a lot of times with polyurethane. You got to remember to do that. You're going to have to do chemical injection first to make the soil non-expansive. Then you do polyurethane injection. You can level it that way, but if your expansive soil is there, there's a good chance for it to go out of level again. So you use chemical injection to neutralize the soil, expansive soils, and then you go out there and do Geotech or polyurethane injection. Here's a pool that hydrostatic pressure pushed out of the ground. Here's another pool that started moving. To build a pool, you dig out a nice hole, compact that subgrade 95%, put in your steel. That's for non-expansive soils, by the way. If you're expansive soils, you may have to go on piers, do chemical injection, removal and replacement. This is the shotcrete, basically it's cement. Shot at the high velocity, added water here at the valve. It's called shotcrete. The way you do design pools in expansive soils, you do remove the expansive soils, replace with non-expansive soils. You go with a structural pool and pier or helical piles on wood spaces, or you use chemical injection. Effects of trees on foundations. We love trees. I love trees. These root systems can affect foundations. Here's a tree kind of falling off due to hurricane. Root systems grow three-dimensional all over the place. This is my house. You got a tree going around it and all through it. It's my vacation house. This is my condo in Florida. My tree house in the backyard. That's a tree hugger. Most people like to have trees around their houses. It's beautiful, but it can cause foundation problems. You make sure you have to remove all the tree roots before you build a house or any building. These root systems, if you left in place, they decay with time. So if you go out there and sock out the concrete and you see all these cracks in the soil below the slab, that's where the roots used to be. Now there are pathways for water to travel. Trees affect foundations in three ways. One of them is called root heave, which tree roots go underneath the slab or the wall, trying to get moisture and start lifting the structure. This is one of our sidewalks downtown Houston. You can see the root systems just kind of destroying the sidewalk. It's a willow tree out there next to a house. And the whole floor slab had moved up 2 inches. You dig next to the foundation, you see a 2-inch root going underneath the slab. This is a house in the Woodlands area. It's a pine tree. The floor slab had heaved up in one of the bedrooms. I didn't know why. They jackhammered the floor slabs to pull the roots out. So a lot of these pine trees, they got surface roots that can cause heave. You can see the root systems under the floor slab areas, the hairline roots. See the root there? You take out the roots, compact that subgrade, put vapor barrier, put steel, pour concrete. Here's the deal that we see a lot of problems in the Houston area, soil heave due to tree removal. The structural engineers need to account for this, because if they don't, it's basically negligence. If you got a site that's got expansive soils, like this site, tilt wall buildings, where the tilt wall panels are coming all out, the site was wooded prior to construction. They cut out all the trees, took out the roots. And as they took the trees out, the soil was so dry after taking the roots out, the hole started heaving up. Here's a tree near point H and point F. Point H is what next to a tree that was taken out. The soils had highly expansive soils there. The area heaved for a period of almost 30 years, about 6.3 inches. Point F is far away, moved about 1 inch. So the closer are you to the tree, the more heave you're going to get. Here's a tree downtown Houston. It's a big tree, about 400 years old. And so if your active zone is 10 feet, this is where your tree trunk is. It just dries up the soil to a depth of 10 feet and a distance twice its height, 2H. This whole area is totally dry. So when you put a foundation here, you got to design for this dry condition. This is the moisture cone profile. The tree trunk sits here to a depth of 10 feet. That's 2H, twice the height of the tree to a depth of 3 feet. All this area is moisture deficient. So when you design foundations, you got to design for the moisture deficient soils. The drip line of the trees is smaller than the root spread. Here's a house in Austin. They cut these 3 trees. The site had a PI between 50 and 60. 3 large trees were removed within 2 weeks. Foundation moved about 8.2 inches. The soil rehydrated, and the whole back of the house starts heaving up. This is A&M research on tree removal. They say if you have plenty of water after 1 year, your soils rehydrates to about 44%. It takes 5 years for the whole thing rehydrates to 100%. So if this tree dies here, this building here is going to move up. It was not designed for the affected trees. If this tree dies or gets cut, this house is going to move up. The fence doesn't say anything. Trees don't know anything about property line. This is the neighbor's tree. If this thing dies, this thing's going to move. If these trees die or you cut them, this building here is going to move. The third way that trees affect foundations is called moisture shrinkage due to tree removal. So what the trees do is, if you got trees out here, this post oak tree next to this building, downtown Houston, this is Houston Community College. And they start sucking the moisture from underneath the building. And you can see the cracks. See the cracks in here? The whole side of the building is dropping because the trees are sucking the moisture out. And the bad problem was this building was sitting on 12-foot piers, which is a floating slab essentially because the piers were not deep enough. So if the trees take the moisture out, the whole building starts dropping, including piers that started dropping. So we call it like basically a floating building. The piers should have been like 20 foot deep, but they're only 12 foot deep. University of Texas did some research. If you put a tree away from a building, if this distance is D and height of the tree H, if D or H is 1, that means the tree is spaced away from a building equal to its height. It can have about 2.4 inches of shrinkage next to the foundation. This area can drop 2.4 inches at UT Austin. Actually, UT Arlington. This is a city of Pasadena building out there. This is their Department of Public Works and the municipal building. You know, basically these big trees suck the moisture out from underneath the slab. See the separation between the slab and the building pad. So different tree species, they got different problems. If you want to have an oak tree, you got to put it away from a building at least 20 feet or 1H away from a building. Same with all the trees. You put them at least 20 feet away. Willow tree 1H, plane tree 0.5 inch, lime 0.5 H, beech 0.5 H, birch 0.5 H. So this presentation indicates trees from hell. Some measurements to prevent tree distress. Put the trees away from the building as much as you can. This distance, preferably probably about 20 feet spacing. Create depressions next to trees so that the moisture does not have to go anywhere to tree roots. They get water here. They don't have to go anywhere to try to get moisture, and they start lifting up the structures. Put sprinkler systems next to trees. You water them so the root systems do not have to travel. When you put trees in the ground, put moisture barriers around them, root barriers. These root barriers makes the roots go slow downward, and they don't go lateral as much. So you plant the trees with the root barrier system. Use a root barrier. We like them to be about 3 to 4 feet deep, maybe 4 feet. You can have herbicide pills, root barriers. The root systems hit them and stun them. Usually they're not very effective. It usually lasts about 10 years. After that, then problems again starts occurring. Put pots next to the building. Here's a Capital One building that had planter areas, but the whole inside the building and outside starts cracking because of the highly expansive soils. This is on Westheimer. So we told them to go out there. See the planter areas. The side of the building starts moving and cracking. They had bed liners here with gravel, bad drainage. Told them to take out this stuff, put in pots in. They took out the planter areas, covered them with concrete, and put pots everywhere. Sewer leak, plumbing leak on old houses and buildings. They got plumbing leaks. As these plumbing leaks occur, the expansive soil starts heaving or shrinking. Basically, it becomes so soft that the whole area starts going down. Here's a leak underneath. You may have to go out there and replace the sewer lines, the sanitary lines, or a plumbing. Here's a tunnel. This is a kind of a water line. The way you do testing, you can do hydrostatic tests, which use it for sewer lines. You fill the sewers with water for about 30 minutes. You watch it to see if it's basically settling. You can do video inspection of the sanitary lines or storm sewers. You can water supply pressure testing. You pressurize it 5 psi above the normal pressure, usually about 40, 45 psi, 50 psi. Hold it for about 30 minutes. And if it's leaky, it starts dropping. You can see the leaks coming out. Here's a video deal. You put it in a kind of a clean out. You put it in and you see on a screen what kind of videos, you got to see roots in your sanitary lines. Non-destructive testing. If you want to know if there's water underneath your building, you put probes in the ground and run current through it. It tells you, here's the probes in there. It's a medical building. You put the probes in. You get a diagram that looks like this. Shows all the water that's underneath the slab. Water's got low resistivity. Concrete's got a high resistivity. It's a pool of water under the slab. Ground penetrating radar, the GPR, and that uses that transmits electromagnetic energy similar to the cell phones, and a receiver also located within the antenna that receives a reflected signal. So you send a signal out and coming back, and it picks up the storm sewers and sanitary lines, picks up the voids. You get a diagram that looks like that. You see where the pipes are. Here's a void in the soil. Here's a building with the GPR on. The blue stuff. The red stuff, deeper voids, high moisture, areas of high moisture, shallow ground void. So the building should be picked up when we did GPR on the building, picked up the voids and areas of high moisture. Geoforensic study of Voss Road. Voss Road had voids underneath it. The way they built it back in the old days, this is the road alignment. This is Buffalo Bayou. One of the arms of the bayou was here. They went in there, filled it up, and put the road on top of it. Well, that fill started settling. So we did GPR testing. We found a bunch of voids under the paving. These are the voids underneath the paving. You can use GPR to see if there's a steel in the walls and the floor slabs, columns, pick up the steel locations. Looks like this. You can also use GPR to check the density of the concrete. Typical concrete, in this case, let's see what we check in here. Soil unit weight. Yeah, the soil. The good soil compact to 115 pounds per cubic foot. Bad soil is 85. See a lot of bad compaction here. Good compaction here. And also with concrete, you want to have a concrete unit weight of 150. These are 150, and here's about 145. Concrete is not as good. You can use infrared because the temperature gradient, you can tell there's moisture problems. Here's underneath the sink. It's a hot water leak there. So you can pick that up. You can see the leak here. Cool, this area is cool. So you can see infrared, pick up the hot water leak. You can also see F.ASCE stucco, large even high rises can be surveyed with it. You see missing columns. You see if there's a missing insulation in the walls. Leak around the light fixture. This is just a cool infrared picture. We talked about geologic faults in Houston. You build structures under the fault, on the fault. The fault goes over here and cracks the parking lot, cracks the building. You see the fault going this way. This is what we call shear zone, up thrown, down thrown section of the fault. The drought causes a lot of problems. We used to have a lot of drought in 2011. The whole Houston, Texas was in major drought, extreme drought. Lake Houston had hardly any water. Lake Travis, no water. Lake Travis, the whole area was like a desert. This is 2011. We had 25 inches of rain, 24 inches of rain. Then in next 2018, we had 56 inches. 2019, 52 inches. 2020, 45 inches. 2021, 51 inches. This year, so far, we have 37.5 inches. We kind of have a drought situation right now. This is the U.S. drought area in 2018. December of 2018. December of 2018. December 2019, Texas got drought areas. See more drought in 2020. This is December 2020. 21, U.S., Texas. 22, we have right now, November, we got U.S. and Texas. This is Texas drought areas. We still got some drought in here, you know, abnormally dry. When you have a drought, the soil becomes so dry, the soil suction, which is a measurement of the affinity of the soil to hold water, drops to about less than 4.5 inch. They call it wilting point. That's when the trees die. If you build a foundation after heavy rainfall, then drought, average rainfall of 50. If you go out there and build a house when it was wet and then you have a drought, you get edge shrinkage or center lift. So you get cracks like that. If you do a foundation, you build a house after a drought and then heavy rainfall, you got a drought in here, low moisture, low rainfall, then you get a bunch of rainfall. You got edge heave condition. Okay. So we got edge lift. This is a subdivision out there near the airport. They have all these channels and ditches here. They just dump soils in it and put it in here. They didn't compact it, and they went out there and built all houses. All these houses cracked up. Here's Eagle Spring. There was a ditch here. They built houses on top of the ditch. Some of these houses had foundation problems. You can see where the ditch used to be from quad map. Forensic engineering courts. Less than 10% of the cases go to trial. Most cases settle after the lawyers make their money. For cases going to trial, forensic engineer plays a major role. It's very important to look at things. For example, Mount Rushmore, this is the front of the Mount Rushmore. And you got to look at things from different perspective. This is the back of Mount Rushmore. If you got projects with good pictures, send them to me. I use them for presentations. We appreciate that. These presentations are going to be on YouTube. You go out there and to YouTube and search Geotech Engineering and Testing YouTube channel. And you'll see the presentation there. There's a program evaluation here. Please tell me what you think of the presentation. If you need to reach me, My email is d@geotecheng.com, 713-699-4000. You're gonna get your continuing education certificates next couple of days. Our next presentation is at F.PTI in December 14th. Geotechnical considerations for design of construction of bridges. You're going to get your PDH hours in the next couple of days. Questions? I got a question here. When removing a tree near buildings, are there ways to minimize eventual heaving? Yeah, if you go out there and do chemical injection, you can reduce the heaving, future heaving, but again, that would reduce your movement. You do chemical injection. Positive drainage, but other than that, when you take a tree and if the soil is clay and expansive soils, it's going to heave up. It's not going to anything happen if you got sandy soils. Questions? Well, I appreciate you all time. You got the poll. Please answer the question on the poll. Thank you. I appreciate that. Thanks. Good. Can you expand sprinkler system across the soil types, keeping the sprinkler system away foundations versus regulating the soil moisture? Yeah, well, you either put more, I suggest if you put more sprinkler systems around the house or a building, make sure you put it all around. Make sure the whole area stays wet. And if it dries up, it's going to start, basically shrinking if you got expansive soils. This is all applicable to expansive soil types. If you don't put sprinkler systems around the building, you got a problem. It's going to basically move depending on cyclic rainfall and moisture changes during the cycle of the summer, winter, fall, and spring. More questions? What was your YouTube channel again? You go to YouTube and you search for Geotech Engineering and Testing, and you go to videos, and all these presentations are on there. There's like 20 presentations. So you go out there to YouTube channel. Any other questions? Thank you. Well, that's good. Thank you.